Okay, next we're going to see how to define functions. So we always define types before functions or terms, right? Because we need types to be able to have functions or even constants, right? So we need the natural numbers before we can have addition. And this is exactly what we do here. So the syntax is similar again to functional programming languages like ML, Haskell, and so on. So you have equations, each on their lines. You have pattern matching on the left, right? So here add is defined as taking two arguments. And here the first argument is simply m. So we're doing pattern matching. We're saying it can be arbitrary. The second argument has to be 0. And if this is the case, then we return m. Otherwise, if we're in the case where first argument is arbitrary, we call it m. The second argument is of the form successor of n. Then we return the successor of addition. And this is the traditional recursive definition from functional programming languages. And here we see if I evaluate, this is a new command, hash eval. If I evaluate 2 plus 7, it returns 9, which is good. I can also use reduce. So reduce and eval are more or less the same for the purposes of this course. There are cases where one or the other will not work, and then you can use the other one. But I think for everything we do, at least one of them will work, thankfully. And eval is usually faster, both faster to type because it's only 4 letters, but also it evaluates the terms faster. Although here, that really doesn't matter. Okay. Then we define multiplication a bit in the same way. And you see when we don't use a variable on the right-hand side, we can use a placeholder, but I could also call it m if I wanted, it doesn't matter. Okay, or I could call it n, so it doesn't have to be the same name as on the following line, right? So something multiplied by 0 gives 0, and something multiplied by successor of something is, well, you continue recursively with the multiplication and then you add m. So again, this is pure, either algebra or functional programming. And here we can evaluate 2 times 7 is 14. We can also use the command print to print some objects, but here it's not very informative. It tells us that mul is defined as mul.main. And this is what it does when there's pattern matching. And if we print mul.main, then we see something quite horrible. Well, this is the actual logical definition under the hood that encodes this recursion. But we're not going to go that deep. The important thing to see here is that Lean has a very solid logical foundation, and all the definitions we do are translated and given to that logical kernel and checked, so that chances are very low that there will be a bug, that will prove something that's not true. And it has a very robust architecture. Okay, we can continue like this. This is a power function. Right, again, 2 to the 5th is 32, that works. Here's a different definition. So here you see, I say power has type not to not to not, takes 2 arguments. I can also take the first argument and move it to the left of the column, right? And then that means it's fixed and I don't need to repeat it every time, right? So in particular here, I don't repeat it. You see, I don't have the m here. I'm not even allowed to put an m here. So Lean gives some weird errors, right? And also I shouldn't put extra arguments here, right? So here, when you put parameters on the left-hand side of a column, then they're fixed for the entire definition. And we saw that already when we defined lists. And it's the same story here. And it's very important. It's a very tricky little point of Lean syntax. So parameters go on the left-hand side, and they are actually called parameters when they're there. And on the right-hand side, you have other arguments like this one. And here we pattern match. You see the column indicates where we start to pattern match. So we pattern match here on the natural number that is there. Okay. We also have some information at the bottom that we don't have to use tooltips if we want. Here's an even more complicated example. So I defined a function called iter that iterates a function, and I can use that function to implement power. So here's an implementation of power that uses a lambda here to, and it gives 32 as well. So this is the right stuff. So this one is a bit more complicated, but if you've done some functional programming, it should be quite natural. You must have seen operators like this. Sometimes they're called power or fun pow or fold. This is a typical fold, okay? Now we look at functions that operate on lists. So the first one we want to have is the possibility to append one list to another. And this is the, well, this is the append function. So it takes two lists as argument, returns a third one. And append takes a type as an argument, right? So the alpha here, because it's a polymorphic function, right? So if I remove this, if I forgot that, then it wouldn't be happy because, well, the message is not helpful as usual. But what we see here is that we have these alphas on the right that are not bound, they're not declared, right? So where do they come from? Well, the best place to put them is here. So we're just going to say alpha \a is how we can get it, is a type, okay? And then we can check this is the actual type of append. And you see it has this parameter alpha at the front, but it also has the Greek letter pi. So for the moment, you can think of it as a synonym for parameter, right? So it's, pi is the p of the Greeks. But again, this is syntax that I'm going to explain in the third lecture, so you don't have to worry too much, just a little bit. And here I show how I can append two lists, right? So the lean lists support a nice bracket syntax, right? So you can write this list of 2 items has 3 followed by 1, and then I append it to a 3-item list, and I obtain a 5-item list. And what is this underscore here? Well, this underscore is a bit boring. It's the alpha over there. So the very first argument of append is the alpha, the parameter. And then the second one is a list. The third one is a list. But I don't want to specify the alpha. I want lean to infer it from, for me, just from the fact that this 3 here is probably a natural number, right? So if I write not explicitly, well, it doesn't like it. Cannot put it there. Regardless, I think the type it infers here, okay, won't print the type, but I know that it's going to be actually the same as if I wrote not, okay? So we see a bunch of aliases here. So square bracket is a synonym for nil. We haven't seen this one yet. Colon, that's a synonym for cons. So that's quite convenient when you start building longer lists instead of cons with parentheses and so on. And then especially the square bracket syntax with several elements can be defined in terms of cons. And actually there is a mistake here, so I'm going to fix it. At the very end of this, I need to put an empty list for good measure, right? Because cons takes an element on the left and a list on the right. So when you arrive to the last element, you cannot just put it there. You need to put it on the left of a cons, and then you need to put a nil on the right. So I will fix that also in the official version of the file. And here's a slightly different version where we use curly braces around the type argument. And that tells lean to make it an implicit type argument. That means an implicit argument, so we don't need to specify it all the time. We don't need to put the underscore, right? So if you look at the example here, there's no underscore anymore. Otherwise, the example is identical. And if we really want to specify the underscore or not or whatever we like, we can put the @ sign in front, which says disable all the braces and turn them again into parentheses. So we still have the flexibility of supplying implicit arguments if we want in, you know, special occasions, right? So I understand this is a lot of syntax at the same time, but don't worry, it will come back at the exam. I was going to say, it will come back in the exercise sheets, it will come back in the homework, it will come back in the Hitchhiker's Guide if you read it. And yes, it will come back at the exam, although the exam tends not to focus so much on minor syntactic points, but more on concepts. Okay. Then you have another version of the append function that uses this syntactic sugar. It's exactly the same as far as lean is concerned, but now we're using more standard syntax. And once we have append, we can also define reverse. And here I've also used not the append that we've just defined, but I've used the official append from lean, which is plus plus. Right, so this operator is append, but that's the real one. Okay. Then this is the evaluation function I promised earlier, which takes you see takes an environment as parameter. So this is on the left-hand side of the column, so it's going to be fixed, and it takes an expression and it returns an integer. Right, and then we have the 6 cases. So for an integer, for a number, we just return the number. For variable, we need to look it up in the environment. So the environment tells us for a string which integer goes with it, which is exactly what we need. We need an integer. So we apply the environment to x, right? So this is higher order functional programming here, right? So the first argument of eval is a function, and then we apply that function to a value and then get another value. And then the last 4 cases are straightforward, right? You just evaluate recursively the 2 arguments, and then you apply the corresponding lean operator, plus, minus, times, divides. And then there's a little warning here, which is everything we've written so far has worked, but sometimes you might write a function that goes beyond what lean can process, because lean will check termination. It doesn't like functions that don't terminate, because these could be logically dangerous. So for this reason, I mean, the course will stay within a fairly reasonable fragment, but don't be too surprised sometimes if you try a definition and then lean complains that it doesn't see why it terminates and so on. So then it just means, well, maybe you need to reformulate it in a simpler way or ask for help.